Welcome to my talk, Tilt-to-Length Coupling in LISA Pathfinder with takeaway messages for LISA. My name is Marie-Sophie Hartig. I'm from the Albert Einstein Institute in Hanover, and I'm giving this talk also on behalf of Gudrun Wanner and Nikos Karnesis. Let me start with saying a few words about tilt-to-length coupling. Tilt-to-length coupling is the unwanted cross-coupling of test mass and spacecraft motion into the phase readout. Tilt-to-length coupling is a crucial noise in LISA. It's virtually not possible to build LISA insensitive to this effect. That's why we need to gain as much knowledge about this coupling as possible. And this is where LISA Pathfinder comes into play. I'd like to start here with a very brief overview about what has been done so far. During the mission, in-flight realignments of the test masses have successfully reduced the noise, but it was still limiting the accuracy between 20 and 200 MHz. That's why this noise has been subtracted in post-processing. Successfully, but however, there has never been a consistent model explaining the data or giving a detailed realignment information. And that's why updated models have been evaluated, but at some point they all failed. As you can see in this plot, where the yellow curve, the noise curve, is just as large as the model itself. We continued on modeling tilt-to-length coupling for LISA Pathfinder. Therefore, we considered all optical path length changes due to shifts and tilts of the test masses and the spacecraft, hence the optical bench, that are orthogonal to the beam propagation axis, which is the x-axis in LISA Pathfinder. And we computed the wavefront-related effects that also couple into the phase measurement. The initial model considered a simplified piston effect, which is defined as the subtracted or added path length due to an offset of the point of reflection due to a shift and or tilt of the reflective surface. And it considered the beamwork on the second test mass due to the lever arm effect, which is the path or path length change due to a rotation about the point of reflection. However, this is not a full description. During my PhD, I added several other extensions to this model. First of all, I added the full lever arm effect, which does not only result into a beamwork on the second test mass. And also, the piston effect is much more complex, especially when rotating about the center of the spacecraft, and we are having hence a large longitudinal offset between the point of reflection and the point of rotation. I also added the effect of transmissive components along the beam path, and this effect can have the same magnitude as the piston effect. Furthermore, I also computed the wavefront-related tilt-to-length coupling and extended the old equation by this one. This extension included also a coupling between the dimensions and the orientation of the measurement beam that is not perfectly orthogonal to the beam propagation axis. To verify my model, I tested against the results provided by the simulation program EFOCAT. And for tilts up to 150 microradian and shifts up to 150 micrometer, the deviation between the simulation and my model, or the second Taylor polynomial of it, did not exceed the picometer regime. That's why we took the model and tested it against the LISA Pathfinder data. And this is still work under progress, and we hope to present the results on this soon. However, we cannot promise perfect results for several reasons. First of all, the measurement accuracy of the beam parameters, the waist size and the distance from waist measured as a detector, are technically limited, and this affects the stability of the coefficients. What does it mean? Our model looks basically like this. It's the sum of coupling coefficients that are depending on the setup, but also on the beam parameters, times the jitter parameters that are the shifts and or tilts of the spacecraft and test masses, a combination of these. And if we now vary our beam parameters by up to 10%, which is reasonable, this leads to a variation of the coupling coefficients by even more than 10%, making our model unstable. We cannot solve this issue by fitting the beam parameters, since the coupling coefficients are much too complex. Neither can we guarantee a successful fit of the parameters C for inserted beam parameters, since the parameter space is still too large. Besides that, if the jitter injections are small, as they have been during the long crosstalk experiment in LISA Pathfinder, we likely overlook the quadratic characteristic of the coupling, and hence fitted models might be not consistent. Moreover, we did not measure the longitudinal positions of the test masses during the LISA Pathfinder mission, and hence this leads to an ambiguous interpretation of the test mass and optical band shifts and or tilts. Last but not least, is there any other effects that we haven't thought about yet? So what does it all mean for LISA? I give the bad news first. It's likely not possible to fully explain tilt-to-length coupling in such missions using formulas. Tilt-to-length coupling was already complicated and hard to model in LISA Pathfinder, and it will be much more complex in LISA. There we will have beam clipping, diffraction, and to use the long arm interferometer output at all, we have to run it through TDI first. Furthermore, the tilt-to-length coupling coefficients are time dependent and hence vary over mission time. And as I said at the beginning, tilt-to-length coupling is a strong noise effect in LISA, so we have to care about it. How's it done? We have to give our best to suppress tilt-to-length coupling already by an intelligent design. Therefore, for example, imaging systems have been implemented to suppress the geometric tilt-to-length coupling or a mixture of geometric and non-geometric tilt-to-length coupling, depending on the choice of alignment effort. Furthermore, also important is the calibration on ground and, much more complicated, but we should keep this option open, also in space. But therefore, we need to study tilt-to-length coupling further and learn how to disentangle the many effects. But there are also good news. When investigating the power spectral density plots for the X1 and X12 interferometer during the long crosstalk experiment, an experiment on LISA Pathfinder to explicitly measure tilt-to-length coupling, we see in the X1 plots clearly peaks at the injection frequencies. So, we might be able to calibrate the test mass interferometer tilt-to-length coupling directly from the raw measurement without TDI, but that only holds for the test mass interferometer, not for the long arm interferometer. Latter is dominated by the laser frequency noise, making TDI essential. And furthermore, we see in the X12 plots peaks at the double injection frequencies, demonstrating that second-order effects are not negligible. With this, I would like to thank you for your attention, and I'm willing to take any questions, so please don't hesitate to contact me. And I would like to recommend following pre-recorded talks. EFOCAT, a software library for simulating precision laser interferometer by Tim Hase. He is introducing the software or the simulation software I used for my verifications. Optical simulations for LISA at the Albert Einstein Institute by Megat RW. She is, besides others, theoretically investigating imaging systems in LISA. And development of 3 degrees of freedom interferometer for tilt-to-length coupling investigation by Yong-Ho Lee. Thank you and goodbye.